Okay, so this is lecture 8. We're going to do Cartesian products and relations. Yes, there's 2 handouts today, which is all of next week's handouts as usual. So that's, well, it's lecture 9, lecture 10, and workshop 5, and another sheet with notation about functions. So those are the 2 handouts today. And yes, there's 4 boxes to put your coursework in, ordered by surname, which will make it a bit easier, hopefully, to find when we give it back. Okay, so what's a Cartesian product? So first of all, I'll just remind you that you hopefully know what R squared is already, which is a set of, which you can think of as ordered pairs, things with 2 coordinates, where the first coordinate, x, is in R, and the second coordinate, y, is in R. Okay, so it's ordered pairs with coordinates, and both coordinates are required to be real. Okay, now there's a very special case of what's called a Cartesian product, where you just take any old pair of sets, A and B, and you do the same thing, but you insist that the first coordinate, x, has to be in A, and the second coordinate, y, has to be in B. Now, maybe, and usually for us, A and B will be subsets of the real numbers. But A and B can be any sets you like, and you can always form a new set from 2 old sets in this way. Notice there's nothing to do with multiplication in here. It's a bit unfortunate, but I gave you a notation for A plus B earlier, which had something to do with taking sums. And now I'm giving you a notion for A times B, which has nothing to do with taking products, nothing to do with multiplying, okay? This is what's called the Cartesian product. It's a sort of way of multiplying the sets together, but it's nothing to do with multiplying numbers together. So you take 2 random sets, maybe they're sets of real numbers, and then, as I say, what it means is we're going to have some restriction. We're just looking at lots and lots of possible ordered pairs, but we restrict what the first coordinate is allowed to be and what the second coordinate is allowed to be. The first coordinate has to be in the first set, and the second coordinate has to be in the second set. But you don't have to use x and y. Those are dummy variables. So I'll note that that's equal to, also equal to, pairs AB, where A is in A and B is in B. Okay, because A and B are dummy variables here, it doesn't matter whether you use x and y or A and B. It just means those ordered pairs where the first coordinate's in A and the second coordinate's in B. Right, so, yes, as I said, it's nothing to do with multiplying real numbers. There can be any sets at all, and it's very different from what we did before when we were adding sets together. It's nothing like that. So let's have a look at a Cartesian product of 2 subsets of the real line and see whether you've got the idea. Okay? So what I suggest you do is you try and think about what this might be, and if possible, sketch it. Because in this is such a concrete setting, you can actually sketch the set you get. So my first set, A, is the closed interval 1, 2. That's every real number, that's the real numbers between 1 and 2 inclusive. And my second set, B, is the real numbers that are between 2 and 4 inclusive. That's our standard interval notation. And now you have to figure out what is this Cartesian product. So is it the closed interval 2, 8, a subset of the real numbers? Is it a triangular subset of R squared, a rectangular subset of R squared, or a spherical subset of R cubed, or you can ask me to explain the question again, and so on, all the usual things. I'll give you about 2 minutes to try and figure out what this is, sketch it if you can, and hopefully after you've done that, you'll be clear what the Cartesian product is. I'll just remind you that our definition of A cross B is a set of all ordered pairs, AB, where A is in A, B is in B, or you could do it as X, Y, or any other pair of letters you like. Okay, so you talk about that for a couple of minutes, see if you can sketch what this set should look like, and and then we'll get votes. You can vote whenever you like. I've zeroed the votes already. Okay, so I'll pause the capture and give you a couple of minutes. Got 34 replies so far. Replies. Replies are coming in slowly. If you want to vote, please vote soon. I'm now going to show you what you've gone for. "44 responses with a big majority for C. So there are, let me just go through it and that will hopefully clear up what's going on. Okay, so C is correct. And as usual, it's a question of figuring out the definition. We just carry on here. You see, we know what A and B are. So this is X and Y under the restrictions given. Means that X, Y, where, so X is in A, that means 1 is less equal to X is less equal to 2. And remember that comma means that we're putting another restriction on, so we can think of it as an and here. And Y is in B, so Y is between 2 and 4 inclusive. And you can sketch that. I'll probably get it wrong because I always get the scale wrong. Let's see. So I want to be able to go between 1 and 2 and between 2 and 4. So let's see if I can do something reasonable. Okay, I'll put some guidelines in. These guidelines are not in the set. This is Y equals 4. That's Y equals 2. This is X equals 2. This is X equals 1. And the region we want is right in the middle of those. So A cross B is a shaded region including the boundary, so I'll put that in as well. A cross B is a shaded region including the boundary. Okay, well, any questions about that example? Then hopefully that will give you a feeling of what happens when you take two sets and take their Cartesian product. A and B were intervals, sort of one-dimensional sets, and when you took the Cartesian product, you ended up in 2 dimensions. If you take a one-dimensional set and take its product with a 2-dimensional set, you normally end up with a 3-dimensional set, and so on. So that's the sort of thing you can expect. Of course, in the full abstract setting, you just get a set. You take a set and another set, and you put them together, and you get another set. But at least in this setting, it was concrete enough that we could do a picture. Right. Now, this exercise is on the practice with definitions, proofs and examples sheet. If you want to know whether A cross B is empty, that happens if and only if at least one of the sets is empty. Now, you don't need both of the sets to be empty to get the product empty. It's a bit like something we had before. If either of the sets is empty, then there's nothing available in that coordinate, and you can't form any pairs at all, no matter how big the other set is. Okay? So that's the way that one works, but it's an exercise for you to do it properly, because it's an if and only if statement, which means there's a two-way implication, and there's something to do. Now, we're mostly going to pay attention, in this lecture at least, to where the set is the same as itself. So I'm going to take a product of A with itself, which the empty set I list here, the empty set is also equal to the empty set cross the empty set. But remember, the empty set's a subset of everything. So I can always put empty set as a subset or equal. It's always true, whatever situation I put it in. Okay, so the empty set cross the empty set is equal to the empty set. It's a subset of n cross n. That's pairs of natural numbers. That will form a nice grid of points in R squared, where the coordinates are positive integers. That's contained in z cross z, which is a more extensive grid, because you allow negative integers, or one of the integers, or both could be 0. So this is the one where the coordinates both have to be integers. Q cross Q, that's points of R squared where both coordinates are forced to be rational. And then R cross R is, as usual, the whole plane that you're used to, R squared. And since R cross R is the same as R squared, it's traditional to say that A cross A is the same as A squared, though I'll probably often just leave it as A cross A. If I do say A squared, in this setting, I'll mean A cross A, but it might be clearer to talk about A cross A anyway. Now, if you've got a Cartesian square, you can look at some subsets of it. Now, R squared is a Cartesian square. It's R cross R, right? So don't forget R squared equals R cross R. So that's a Cartesian square. And inside that, I could look at a set of points. M is the set of pairs x, y, and r squared with the restriction that x is less than or equal to y. Now, you can sketch that. You start by sketching y equals x, or x equals y. Should go through the origin if I don't miss. So this is the y-axis, x-axis. That's y equals x. And you have to decide where m is. Now it extends in all relevant directions. It extends off infinitely. It doesn't stop. So it's rather difficult to draw the whole thing. But at least we've got some idea of where it is. This is x equals y. X small root of y is going to be left of it. Or you could say y greater root of x is above it, which curiously gives you the same thing. So if I sketch that in some other colour, what should I go for? Here's this is m up here. And it doesn't stop. So I could draw dots all over the place to show that it doesn't stop, but that would just take me forever, so I won't. Okay, so m is where x is less than or equal to y. And that's a subset of R squared. It's a set of pairs. Now we get the following connection between m and less than or equal. If you take real numbers x and y, and you look at the pair xy, then xy is in this thing m, if and only if x is less than or equal to y. That's how we set it up, right? So we've drawn a picture, and the picture represents x less than or equal to y. You could use less than or equal to define m, but if you knew what m was, you could use that to explain what less than or equal meant. Each one tells you what the other one is. Let's look at another example. So this time I'll look at pairs of integers, right? I'm not going to draw this one, though you could if you wanted. Pairs of integers those pairs so that the difference in the coordinates is divisible by 2. In other words, the difference in the coordinates is even. Now, which pairs do you get? Well, so your pair is in M if and only if M minus N is even. What that means really means, so there's all this stuff about same remainder when you divide by 2. If you divide by 2, you get remainder 0 or 1. If you get remainder 0, you're even. If you get remainder 1, you're odd. For M minus N to be even, they have to have the same remainder, and that's the same as saying either they're both even or they're both odd. If one of them's even and the other one's odd, then the difference will be odd and it won't work. Now, this is a particularly important example of a relation called Congruence modulo 2. Okay, so if I write M, 3 lines, pronounced congruent, N, so this is pronounced M is congruent to N modulo 2, or mod 2. All it means is that they're either both even or they're both odd. Or you can think of it saying they've got the same remainder mod 2, or you can use the definition here. That's when M minus N is even. Now that's an example of a relation, and we're going to look at lots more relations of this type, well, and similar to this. We won't just do modulo 2, we're going to do modulo other positive integers. Same remainder when you divide by 9, same remainder when you divide by 11. Each of these things gives you a different kind of relation on the integers. Okay. So we'll come back to that. So now you take any set. This is going to be a very abstract bit, I should warn you. Here's the very abstract bit, but we'll get concrete again in a minute. So you take any odd set, and you take any subset you like of S cross S. And now for each pair of X's and Y in this set, which so far have been nice things like the real numbers and integers and things like that, you can ask whether that point x, y is in your set. Like we asked whether the point was in the shaded region I had earlier. Okay? Then we can bring in a notation, R, which I'll pronounce as x is related to y. The funny thing is, it doesn't matter what letter I use here, or indeed, you can use almost any symbol here, as long as you explain that you're talking about introducing a relation. And here, what I'm going to mean by x is related to y means that the pair xy is in this set we're looking at. So earlier, what that means is, xy was in that shaded region, that meant x is less than or equal to y, which means R was just less than or equal. So that's what the earlier relation we had was. And then you can put a line through the R to mean that it's not in that set. Now, in the earlier setting, that would be x not less than or equal to y, which would mean x is greater than y. Or, in other words, xy was in the unshaded region. R is then called a relation, sometimes called a binary relation on the set S. We'll just call it a relation. And that's very abstract, but usually we use a practical rule. Okay, so whenever I tell you what a relation is in this module, I'll always give you a practical rule, not some weird set. Okay, so I've told you, we know what less than or equal means already. I've told you what congruence modulo 2 means. It means that M minus N is even. So I'll always give you a practical rule, but in the pure mathematician's definition, if you want to know, if someone says, what is a relation, it might not be satisfactory to say a relation, well, it's something like less than or equal to, or less than or equals, or something a bit like that, some sort of rule. You might not be happy with that as a pure mathematician. So in fact, what we've seen is that relations and the sets of pairs they correspond to are closely related, and you can use each one to determine the other. So if you want a rigorous definition, you would start with the set M and say that relation comes from that. And in fact, in the literature, formally, they say that it's a set of pairs that's a relation. And we just use R as a notation. But that's very abstract, and so we're going to pretty much ignore that formal definition, and I'll just keep giving you practical rules that tell you when things are related. So I'll say things like, suppose the relation means this, check what properties the relation's got. Okay, so here's lots more examples. So we come back to practical rules, okay? So here they are. If you look at R, or any subset of R, you can use any of these well-known things to define relations, okay? So you've got 2 equals 2. 2 is not equal to 3. Now, notice that not equals is already a relation, but it also comes from equals by putting a not sign through it. So you can think of not equals in 2 different ways. One as being a relation on its own. Another one as coming from equals, but putting the line through it to say that you mean not equals. As we know from before, we have 2 is less than 5. 2 is also less than or equal to 5. 2 is not greater than 5. Now, no one ever writes not greater than 5, okay? But you could, because greater than is a relation, so you could put a line through it and get the not greater than relation. You wouldn't normally do that because not greater than means less than or equal. And so on, okay? So you can do this sort of thing, and that gives you lots of relations. You can use the equality relation and the not equality relation on any set. It doesn't have to be a subset of the real line. That works because equals and not equals make sense whatever set you're dealing with. For natural numbers, we have the divisibility relation. This is the one which says that n is divisible by m. Remember, this vertical line is a nice binary relation. But you remember it means that it may be, you have to remember which way around it is. So that's if and only if n over m is in Z. But of course, I defined it on the natural number, so actually, if n over m is in Z, then it's actually a natural number. Or whichever other version. So this is n is divisible by m, or m divides n. Maybe I should call this the divides relation rather than divisibility relation, because it's somehow the wrong way around. But I think everybody calls it the divisibility relation. Okay. And then, of course, you can put a line through divisibility to get the non-divisibility relation. So you've got things like 2 divides 6, 3 divides 6, 4 does not divide 6, and I suppose not divides would be divides, but you wouldn't want to put a line through the not divide symbol. It would look weird. But yes, 4 does not divide 6, so that sort of thing. Okay. I don't think you want to put a line through that one. So here's another question for you. You've got a relation on the set Z. It might be one of the ones we mentioned already. And I want you to look at the statement, 1 is not related to 1. And I want you to decide, and don't do it yet because I need to zero the votes. Hold on. It's telling me that themes cannot be loaded at the moment. I don't know what that means. Okay, so the question is there a relation on Z that makes this true or not? So is it never true, always true, sometimes false? Please explain the question again and all that. Okay, I'll just give you a minute to chat about that and see what you come up with. Okay, so C is the most popular answer. Sometimes true, sometimes false, depending on the relation, which is correct. For example, if R is the equality relation, then 1 is related to R, and 1 is related to 1. But if R is the not equal relation, then 1 is not related to 1. And I heard some people discussing various other relations like the less than relation. If you use a strictly less than relation, then 1 is not less than 1, so 1 would not be related to 1. If you use a less than or equal relation, 1 is less than or equal to 1. So you could use less than or equal. 1 is less than or equal to 1 because it's less than or equal, so it's okay. You could use that. And so on. There's millions of examples. Now we move on to a very important relation, which we'll keep coming back to, which is called congruence modulo k. We already did k equals 2. So this was when k equals 2, it was if you leave the same remainder when you divide by 2. Same works for k. Think of k equals 9, k equals 10. K equals 10, it's actually particularly easy to see what the remainder is when you divide by 10 because it's the last digit, for a positive integer at least. So for a positive integer, if you want to know the remainder when you divide by 10, it's just the last digit. So then congruence modulo 10 means same last digit for positive integers. Negative integers, you have to mess around a bit, right? -1 and 9 are the same modulo 10. They're congruent modulo 10. So modulo 10 is easy. So 19 is congruent to 39 modulo 10. But also -1 is congruent to 9 modulo 10. Because you just need 10 to divide the difference. So the negative numbers are going to start having a different last digit. They're going to be minus something ending 1. The positive ones will be something ending in 9. The negative ones are going to be something ending in 1. And they'll all be congruent to each other, modulo 10. Okay? We're going to be looking at modulo 9, modulo 11, things like that, as special cases as well. And if you want to find out more about it, this is often called clock arithmetic or modular arithmetic. And it's great fun. Okay, I found out about this before I came to university, and I thought that that's what I was going to spend my life on because it was such fun. But in the end, I got involved in epsilons and deltas instead. But that's life. Okay, then let's have a look at sets of sets. Here's an example of a set of sets. Okay. This set S has got 4 elements in, and each of the things in S is a set. Now, some of these sets are subsets of the other ones, and some of them aren't. So you can use subset or not subset to be a relation on S. And, of course, you could do not a subset. So you get things like 1, 2 is not a subset of 1, 3. But 1, 2 is a subset of 1, 2, 3. So you can see we can compare these sets of each other, and some of them will be subsets of the other ones, and some of them aren't, and so on. And that gives you a relation on S. But there's nothing special about this set of sets. Whenever you've got a collection of sets, and if I say a collection of sets, that just means a set of sets. It's just that it sounds a bit strange to talk about sets of sets, so mathematicians introduce words like collections and families and so on, just to keep track of what level you're at. So we often talk about collections of sets, but it just means a set of whose elements are sets. So this is a collection of sets. Any collection of sets you take, you can use these relations on that, and it'll give you a pair of relations. These are sort of inclusion relations. You could also do them the other way around, by the way. There's also these pair of relations as well. This is the superset relation, which means that the thing that's mentioned second is a subset of the thing that's mentioned first. That means the first one's a superset of the second, but people don't talk about supersets as often as they talk about subsets. And this is not a superset relation. It's not as simple as being able to swap them round, unfortunately, because it's not as good as less than or less than or equal. Oh, and there's also proper subset. I won't bother with proper subset. Now, so what are the extreme settings here? You take a set S, and you want to put a relation on S. That means you need a subset of the Cartesian square. Okay, well, there's two very extreme examples of subsets of Cartesian square. One is you take the whole of the square, all of S cross S, and the other is where you take nothing at all, the empty set. They're subsets of S cross S, and every subset of the Cartesian square gives you a relation, and these two are particularly extreme ones, and they've got names. You might think that the equality relation is extreme. It's quite extreme, the equality relation, but it isn't either of these. The equality relation gives you the diagonal. It's where y equals x. So that will give you the diagonal in your product, okay? But that's not, the diagonal is probably not empty, and it's probably not the whole thing, okay? Unless S is empty. So if you take the whole of S cross S, then the relation you get, and it really doesn't matter what letter you use. We sometimes use R, we sometimes use rho, we sometimes use all sorts of other symbols. You can use rho, you can use R1, R2. If you've got several different relations, you can give them different numbers. You could use a sort of wriggly line. It doesn't really matter what letter you use for the relation, okay? But whatever letter you use for it, if it came from S cross S, it means that everything is related to everything else. That's not very exciting, so it's called the trivial relation. The trivial relation is where everything is related to everything else. The other extreme is when nothing is related to anything else. It means not related gives you every pair, and related gives you no pairs at all. There are no related pairs. Nothing's even related to itself with this one. So it's even worse than the equality relation. You're not even related to yourself with this one. And that's called the empty relation because nothing's related to anything else. And as I've said, you can always put a line through your relation, though the notation is sometimes hard to read. But whatever relation you've done, you can put a line through it, and that's another relation called the complement of the relation. Because you get it by taking the complement of the set of things that were related. The things that were related before are now not related using not are. Okay? And it feels like we're stopping in the middle of something. I remember the first time I gave this module, I had planned to go on from here, and I realised that it wasn't time. So we are really stopping in the middle because I want to go on and really talk about equivalence relations and special kinds of relations and partitions. We'll be doing that next lecture. But for now, we'll stop there, and we'll start the workshop at 4 o'clock.